A new navigation lock is being constructed by the Nashville District of the Corps of Engineers and the Tennessee Valley Authority near Chattanooga, Tennessee. A new modern lock, 600 feet long by 110 feet wide, will replace an outdated and deteriorated 360-foot by 60-foot lock built in 1940. The existing lock continues to experience severe concrete deterioration from alkali silica reactivity, which will force the facility to close by the year 2012 due to structural instability and equipment misalignment, resulting in frequent lock closures for repair. The existing lock currently has the longest lockage time on the Ohio River system, roughly 8 hours for a full tow of 15 barges, one jumbo barge at a time. The new lock will permit tows of up to 9 jumbo barges to be transported through the facility in a single lockage. The new lock will be located downstream of the existing gated dam structure and riverward of the existing lock. The river step at the lock will remain at roughly 50 feet, and the new lock will replace 4 gate bays in the dam. The downstream approach channel remains between main piers of the railroad lift bridge, and guide and guard walls will be included both upstream and downstream. The existing lock will be closed off with a new dam section to maintain the line of flood protection. The new lock has an estimated construction cost of $325 million and was authorized by the Energy and Water Development Appropriations Act of 2003. Funding is provided by 50% federal appropriations and 50% from navigation user fees collected in the Inland Waterways Trust Fund. Site construction began in 2004, and if funding streams permit, will be completed by 2012, when the existing lock is scheduled to close. In order to facilitate the construction of the new lock in a more timely and cost-effective manner, the Nashville District and their design consultants, Bergman Associates and Ben C. Gerwick, have turned to the use of innovative in-the-wet construction techniques for portions of the design. Concept studies were performed by the Bergman-Gerwick team in 2003 to evaluate the benefits and cost savings of using either lift-in or float-in construction methods. This study showed either lift-in or float-in were viable alternatives to conventional construction built within a large dewatered cofferdam, and that there was potential for cost savings with the innovative construction methods. The innovative design methods were also determined to have significant benefits to navigation during the construction of the new lock. With the relatively narrow passageway from the existing lock between the shoreline and the land wall of the new lock, to have the minimum intrusion into the navigation channel during the lengthy construction period would be a distinct advantage. With the use of a conventional cellular cofferdam, the clear distance from the guide wall to the cellular structures would be only roughly 60 feet. However, using lift-in or float-in construction, the channel clearance from the guide wall would be roughly 90 feet, an improvement of about 30 feet. Also, using large precast segments for lift-in or float-in methods could reduce the number and duration of lock shutdowns during construction, as each installation could be performed in a matter of days, and primarily from the riverside. Each day of existing lock closure would be very costly to the navigation industry, and the savings by using innovative construction could be substantial. In 2004 and 2005, concurrent studies were made to further compare the advantages and disadvantages of using in-the-wet construction to those for conventional construction for the large lock cofferdam. Difficult foundation conditions resulted in complex designs to maintain cofferdam stability during construction for conventional construction. Geotechnical studies for the new lock and cofferdam focused on rock strength, dip on bedding, weak bentonite seams, and seepage. With substantial underwater rock removals adjacent to the cofferdam requiring rock anchor systems for stability, the conventional cofferdam option would likely result in increased risks and costs. The Bergman-Gerwick team design for the landside portion of the cofferdam using lift-in construction was found to have both improved constructability and lower total cost for the lock wall and cofferdam compared to the conventional cellular cofferdam and lock wall, and was slightly less expensive than float-in construction. The lift-in option was then selected for the full landside length of cofferdam by the Nashville District in late 2005. The landside lift-in segmental cofferdam's final design and the preparation of construction documents were performed by the AE team during the first half of 2006 and put out to bid that summer. The segmental cofferdam was designed to connect to the existing lower guard wall and to a conventional cellular cofferdam for the downstream and riverside portions. The planned sequence of construction for the segmental cofferdam consists of various steps to construct both the cellular and segmental cofferdams in a simultaneous manner. Large concrete box segments roughly 40 feet wide, 50 feet long, and 27 feet tall, weighing between 250 and 340 tons, are constructed on a large work barge at an erection facility by connecting large precast panels together on a frame of internal steel bracing. The segments have been designed to minimize weight to allow lifting and positioning with readily available marine equipment. As the segments are fabricated at the erection facility, foundation preparation, partial lower guard wall removal, drilled shaft installation, and construction of the conventional cellular cofferdam will begin at the lock site. Once the segments are completed, they are transported to the new lock site, where marine cranes lift the segments into place over the previously constructed drilled shaft foundations. Installation of the segments occurs one at a time, from upstream to downstream. Land-based surveying, GPS tracking, and alignment devices pre-installed on the segments assure proper positioning. After each segment is set in place and the perimeter sealed to the foundation rock, an impact protection system will be installed to protect against accidental damage from barges in the adjacent navigation channel. Once reinforced Tremy concrete is placed to seal the base of the segment will be dewatered and reinforced concrete placed in lifts to the top of the segment. The interior steel bracing will be removed as the concrete placements progress and reused for other segments. Once the concrete reaches the top of the segment, the cofferdam protection system will be removed and formed concrete added to extend the protection of the cofferdam approximately 16 feet above the top of the precast segment. The top elevation of the segmental and cellular cofferdam is set to the 100-year flood tailwater to reduce the risk of overtopping during construction. This process will continue sequentially for each of the landward segments, while the construction of the cellular cofferdam progresses simultaneously. The connection between the segmental and cellular cofferdams will be made at the downstream end of the landward side. To complete the cofferdam contract, a flooding facility will be constructed, and grout curtains, instrumentation, power, and lighting will be installed. It is expected that the cofferdam will be completed within 3 years of the start of construction. Once the cofferdam is complete, the lock area will be dewatered, and the new lock constructed under a separate construction contract. In that contract, the landward lock wall will be constructed integral with the segmental cofferdam. The rock inside and adjacent to the landward segmental cofferdam will be excavated to allow the remainder of the landward lock wall and its filling and emptying culvert to be constructed. This lock wall construction will be founded either on rock or on drilled shafts constructed within the dewatered cofferdam, depending on the rock quality. The river wall monoliths will be conventionally cast in place within the dewatered cofferdam. To complete the lock structure, gate sills and cross culverts will be built, gate and valve machinery installed, and lock fittings, electrical, and controls added. The cofferdam will then be flooded and the cellular portions removed. Next, the in-the-wet construction of the lock will be completed, the existing dam breached, and upper and lower approach walls added. Once the new lock is complete and open for operation, the existing lock can be decommissioned and the new closure installed across the original lock chamber to extend the dam. The innovative design and construction of the segmental landward cofferdam and integral landside lock wall is the first use of lift-in techniques to construct a large new lock structure in the United States. The main advantages of the innovative approach over conventional construction include less risk with drilled shafts than with a foundation on variable rock and using rock anchors, less rock excavation, 30 feet of additional navigation clearance, no landward cofferdam demolition, reduced impacts to navigation, reduced environmental impacts, cost savings of roughly $10 million for the combined landside cofferdam and lock wall. This innovative design by the Bergman-Gerwick team has helped the Nashville District and TVA with the construction of a new, larger lock that will address the needs of the regional and national navigation industry. The new lock will permit larger tows to be locked through the facility and will reduce the delays for the navigation industry on the Tennessee River. Chickamauga lock replacement has been designed and will be constructed using the latest engineering techniques to ensure an efficient and cost-effective facility.